We can now move to the interaction between the host and the controller. So now we are going to go again through the interrupt mechanism. You should be familiar with it at this point, but before that, let's look also at the alternative way we can have for the CPU and the controller to coordinate. So the first option, this alternative, it's called busy waiting or polling. So in this case, it's the host who tries to continuously access the device, let's say a disk, for example, through the controller, and keeps trying until it actually manages to get access to it. This is an alternative to the interrupt mechanism, in which is the device that pings or sends a message to the host when it is available or when it's done writing or reading data and so on. Okay, so if we go for the first option, polling, we need, of course, to define a procedure with which the host can initiate input or output transfer with a certain controller that is connected to a certain device. Okay, so we have this handshaking procedure. We need at least 2 bits to coordinate the producer-consumer relationship between the controller and the host. So we can use the busy bit in the state to register of the controller. So the controller uses this bit to indicate the state of its current state to the host, right? Basically to say whether it's already performing some operation or if it's free and it can be then used by the host. The host sends signals about the fact that it wants to interact with the controller through the command ready bit. Basically notifies the controller that a command is available, that is ready, and the host would like to issue that command to the controller. And then basically this is going to happen in a loop. So the host, the CPU in our case, will keep reading the status register over and over until the busy bit becomes clear, meaning the device, the controller and the device behind the controller can be used. And now this is not necessarily a bad idea. So if you have a fast device controller connected to fast devices, and there are good chances that you can find the device as free, this actually can reduce time, because if you are lucky and the busy bit is set to 0, so it's clear, you can immediately take control of the device and interact with the device. But of course, it becomes quite inefficient if you have to stay in this loop a lot, and the device is usually busy, because then you're wasting cycles of your CPU trying to get access to it rather than doing something else. And this is why you commonly go for interrupts, which are the alternative to this. Okay, so let's look a bit at the interrupts. It's nothing new at this point. It should be at least the concept. So the CPU has a physical wire, it has a connection, which is called the interrupt request line. And it senses this line after executing every instruction. Okay, this we show in the very beginning. We saw this in the very beginning of the course. If there is indeed a signal in that line, then the hardware, remember always cooperation between hardware and operating system, the CPU performs a save state, okay, and it does a context switch. It jumps to the interrupt handler routine at a fixed address in memory. As we will see, each interrupt is actually a number, and that number can be converted to a specific address where you will find the set of instructions that belong to the operating system and are specific to the interrupt you get. So if you get an interrupt for a page fault, that interrupt will be translated into an address in memory, and in that address you will find the instructions that the operating system uses to handle a page fault. So the interrupt handler checks what is the causes of the interrupt. It does the necessary processing, let's say if it's a page fault, to locate the page on disk. And then the CPU can go back running what it was running before the interrupt. So this is just what I just said. There are different steps here. The CPU is initiating some input/output. It gets to the controller, and the controller, when the input is ready or the output is completed, or if there is maybe another reason to generate an interrupt signal, maybe an error, it will send such a signal to the CPU. And the CPU will react to that with the interrupt handler. And notice that in between 1 and 4 here, the CPU is executing checks for interrupts between every instruction. Okay. Eventually, the CPU will resume the processing of the interrupted task and go back to step 1. So we say that the device controller raises an interrupt by asserting a signal on the interrupt request line. The CPU catches the interrupt and dispatches it to the interrupt handler, and the handler clears the interrupt by servicing the device. As you can imagine, in practice, stuff is always slightly more complicated than what we discuss in the course. So everything we said so far is true, but in practice, there is not a single line for the interrupts, because as you can imagine, not all interrupts have the same importance. A page fault really needs to be addressed as fast as possible, while if the user is striking a key on the keyboard, being slightly late with that does not really make a big difference from the user perspective. So in modern operating systems, there is the ability to defer the handling of an interrupt if the CPU is already doing some critical processing. Okay, and of course, you also need an efficient way to locate the code that is defined by the operating system to handle each interrupt rapidly. Because of course, you always want to minimize the time you spend doing all this extra work to handle the interrupts, because those are cycles of your CPU that you're not using to run a process, but you are using to basically coordinate the processes running the operating system and so on. And we said this in the very beginning with context switches. You really need to minimize this as much as possible if you want to have performance. So you have multi-level interrupts in modern operating systems. So there are high and low level priority interrupts. And there is, of course, dedicated hardware that is going to manage these different priorities and the interrupts in your computer. So practically, you have two interrupt request lines. One is the one of non-maskable interrupts. Okay, so these are serious interrupts, serious events that need to be addressed as fast as possible. And then you have maskable interrupts that can be turned off by the CPU before the execution of critical instruction requests. So basically, you can physically prevent the CPU from checking again for interrupts that are not really important if you know that for a specific period of time, the CPU is running code that belongs, for example, to the operating system to serve a critical interrupt. Okay, for example, an unrecoverable memory error, as we see here in the slides. This is what I said before. So each interrupt actually carries an address, and that address can be translated, or this offset more than an address in that refers to a table of addresses, can be translated into memory address that contains the desired routine to handle to clear the interrupt. Okay, so this is just an example for an old processor. You have here the vector number that is carried by non-maskable interrupts, and here you can see that, for example, if it is 14, then that is a page fault. Okay, so when you get this number, you can go into the table where you keep the addresses of the routines and associate 14 with the routine in the operating system that handles the page fault. And then handling the page fault becomes very fast because you sense the line, you immediately switch to that, and everything is done by the hardware that wakes up the operating system in a few cycles. Now, the operating system can interact with the interrupt mechanism in several ways. So basically, it's up to the operating system which routines are used to react to the specific interrupts. What happens is that when you have to populate this table of addresses that are associated to the different numbers you can get for interrupts, that can be done when you basically boot your machine, because the hardware can probe the buses you have and check which are the controllers, and then share this information with the operating system that can install the corresponding interrupt handlers. Okay. During input-output, hopefully this is clear now, the device controllers will raise interrupts when they're ready for service. Okay, and so the classical examples we made before, the output has completed, or there is input that is available, or maybe there is a failure.